you can then decipher what the phase plane looks like. In fact, it's a little bit more than that, because you have the energy lemma, which says that the solutions in the phase plane have to be constant curves of energy. That's the rest of this story. And so that's why I'm drawing this plot over here. Like, this is the reason I'm doing this is that. So the force minus the force is 2x squared plus x minus 1. So you integrate that, and that gives me the potential energy. So the potential energy here is, oh, come on, where'd you go? Come on. Drive me nuts. Why am I differentiating it? Okay, so g prime of x is 2x squared plus x minus 1, right? Set that equal to 0, we get 2x minus 1 times x plus 1 equal to 0, all right? And so the critical points for the potential energy are 1/2 and minus 1. And so that allows me to draw this picture here. That's the potential energy curve. From the potential energy curve, then I can see what the corresponding plots in the sorry, I should go over here. So the again, the potential energy plot, G versus X, is this. We found there's a critical point at minus 1 and 1/2 from the formula, just factoring. And so that's the it's a maximum potential energy. There's a minimum potential energy. And then the way to find these curves down here, you actually imagine, oh, come on, the energy, what? Come on. If you can imagine, if you draw an energy level, if this is potential energy, the energy level has to be above the potential energy, right? So you just think about drawing an energy level in here. If I do that, you can't go past this point because that would mean you have negative kinetic energy. So basically this energy level corresponds to this curve down here, like that. In here, you get these little stable orbits, periodic orbits. See, it's stuck it's stuck in the potential well between here and here, and that gives you these curves down here in the Vx plane. See, this means that it's stuck. X is stuck between these two extremes, and then like it's going zero velocity at its most extreme x value. Then it goes. Which direction do these go? Well, that you can figure out from the fact that dx dt is v, right? So the solutions flow right when v is positive. So there's arrows missing on here, but basically, you go this is what happens. It goes round and round and round. Corresponding to the fact physically that if your system has energy like here and it starts here, then it just kind of oscillates back and forth like that. On the other hand, if you have energy that's larger than that certain value right there, what's going to happen is if it's going this direction to start with, then it comes in here, it hits the potential well, and it just bounces back and just keeps going and going and going and going, corresponding to something like this solution. Bounces, then just keeps going back that way. So I've done all of this analysis about what possible solutions look like and how the behavior of the system is. Right? If you take ownership of this method, it gives you a way of analyzing physical problems without actually we've not done so much as solved an equation. I don't know what the solution is to the Newton's equation, and yet I can tell you what the behavior of the system is by analyzing these plots. That's the idea. That's the energy method. So anyway, there's that. So now Laplace Transforms. It's Thursday, right? I said I'd talk about Laplace Transforms Thursday. So, come on. Just let me, you stupid thing. Go up. Come on. All right. Why do we study Laplace transforms? So here's the Laplace transform. The Laplace transform of f, all right, of t of s is by definition the integral from 0 to infinity of e to the minus st f of t dt. So that's the Laplace transform of a function. For example, if we calculate the Laplace transform of the number 1, that would be the integral from 0 to infinity of e to the minus st times 1 dt, all right? And so you can do the integral. You'll forgive me if I cheat a little bit here. E to the minus st over minus s, evaluated from 0 to infinity. Cheating in the sense that I haven't written the explicit limit. Don't tell my Calculus 2 students. So that is e to the minus s times infinity over minus s plus 1 over s times e to the 0. Now if s is negative, this thing diverges. Game over. So we need s positive in order for this calculation to converge. So this is in fact going to be equal to 1 over s as long as s is greater than 0. So the Laplace transform of the number 1 is just equal to 1 over s. There you go. That's our first Laplace transform. So engineers tend to call s the frequency domain, whereas, of course, t is the time domain. And you might ask why we're doing this. Well, that will become more clear in the next lecture, but basically Laplace transforms are going to give us this really slick, elegant way to solve problems with discontinuities in them. Real-world problems with discontinuities abound, right? Anytime you flip a light switch. There used to be these things called light switches that you could flip in rooms, right? Like anywhere but here. Now we're too smart for that, apparently. But anyway, there's these things called switches. You flip them. There's this abrupt change, right? A discontinuity. And so the Laplace transform technique will give us a way to solve discontinuous problems in an efficient and unifying way. But at the cost of weirdness. Like, where on earth is that coming from, right? But now I know of an explanation by an MIT professor, and if I can find the link, I'll give it to you. But if you find his explanation convincing, great. It doesn't really matter if you understand it or not. The motivation for it. Really, the point is once we start using it, you'll see why we do it. And anyway, electrical engineers use Laplace transforms a lot in their theory and analysis. So, thanks, guys. So mission 7 due next Tuesday, obviously, due to the election. Wahaha.